Okay. So this is a bit of the LU decomposition. You need to have in general an idea that you have your A, which you translate into LU, your U, you do some Gaussian elimination. Right? You do some Gaussian elimination, and then you get your U, gives you your U, and then the L is nothing but those scalars, right? Where you have M, K1, and so on, N1, all the way. Will then give you your L. And with that, you can do a backward and forward substitution. Even more so, you can do with pivoting or without pivoting.
Excuse me, doctor.
Yeah.
Here, where we were, I want you to go to the first page where we were reducing Gaussian elimination, and then you give us a technique of how to find the lower.
Yeah, maybe I think I'll just solve one critical example, which shouldn't be a problem. We can have let's solve one simple problem so that we all understand how to approach this thing. Okay, so let me say A.
Is it okay if we solve the very problem there?
Which one?
The one that you gave us.
Yeah, so I mean, with that one, you know, we have solved for this one, right? So this here becomes your U, right?
Yes.
And now you have to find the L, and then the L I said is the scalars, right? So your L becomes your L will become, let me come here. So let's go so that we can just maybe redo it. Okay, so we had 1, 2, minus 1, 2, 4, 0, 0, 1, minus 1. Right. Then when we started, we said 1, 2, minus 1, 2, 4, 0. Sorry, we said you do R2 minus 2 R1. And this will go to 0. This will go to 0. This will go to 2, minus 2. And already from other one, so for R3, right? For R3, we just say R3 so we maintain it, right? So this is 2. And here, R3, we have 0, 1, minus 1. We maintain R3. Then the next step swap. We swap 1 minus 1, 0, 0. And here, what we have done is now to use a multiplier, a pivot P, which is 1, 0, 0, 0, 0, 1, 0, 1, 0. So we just keep track of the multiplier, the pivoting. So now this is our U, and then our L is 1, 0, 0, 1, 0, and then 1. And then the only thing we do is that we say, okay, our L in this case, we multiplied we did here, so here, right? We used a 2 here, this scalar here. Okay, and then in the other one, we didn't do anything there. So we have 0, 0. But you shouldn't forget that in this step, right? In this step, we did this, but now for the L, we still need to then multiply by the P to get an appropriate L that corresponds to what we have done with the pivoting. So now we have a 1, 0, 0, a 0, 0, 1, and then a 2, 1, 0, something like that. So
Okay,
if you
that's okay.
if you do that, then now you have an A, so you have a PA, right? Because your PA now is going to be 1, 2 minus 1, 0, 1 minus 1, 2, 4 minus 1, 0. Right? And this should correspond to PW as well. So this is what we mean. PA should be equal to PW. So now we have our U, and then we have this guy here that we can now use.
Yes. Excuse sir.
Yeah, I'm listening.
Please, I am not understanding. Like I want to get a clear view of what is actually happening. What's actually the use of the
Permutation matrix.
upper and the lower, and then the permutation matrix. Yes, sir. Just
So exactly what I said. So if you do if you have a matrix where you cannot do in a clear case like this one, right? This one here. When you do a Gaussian elimination, so first, if you want to do the LU decomposition, you start with Gaussian elimination, right? So maybe just in case, we can start with the Gaussian elimination. So just for a good example, So because you need to understand first you need Gaussian elimination. And then if you understand the Gaussian elimination process, then it's easier for you to understand how you are getting the L and the U. I hope this is clear. So maybe let's take an example of and then see how to do Gaussian elimination.
Yeah.
Because
Excuse me.
I'm just presuming Gaussian elimination is first year, maybe second year linear algebra. That's why I'm not I just didn't bother about it. But let's say 1,
Yeah.
1, 0, 1, or 0, 3. Let's take an example. 2, 1, minus 1, 1,
Excuse
3.
me.
Yeah, I'm listening.
Yeah. Like it's not about the Gaussian elimination, but I want to know what are the uses? How do we use our L, our U, and then probably our the permutation matrix to solve the problem we have. That's just
Yeah, so that, I mean,
going on.
basically, what you do, you have a matrix, you do LU, right? But you have a system. It's a system AX is equal to B. You decompose your A into LU. So if we have AX, then we have this, right? And we have a right-hand side B. And then what do we say? We say that all you have to do is say, if we say that Y is equal to U of X, then we can solve for Y. Then this is 1. Then the second part is if you substitute this to be Y, then the second part is then to solve for Ly is equal to B. Then solve for solve for X here, and then solve for Y here. So basically, once you have this, you solve first, because here this is unknown, this is unknown. So solve for Y in the second equation, then substitute your Y in the first equation and solve for X. This is all. That's in the case where you are able to decompose your A directly into L and a U, right? But in some cases, example is in this case, you see that when you want to do an LU decomposition using Gaussian elimination, at this point, you have a problem, you have a challenge, okay? When you are applying your Gaussian elimination, at this point, you have a challenge. So to overcome this challenge, we introduce this idea of row exchange or column exchange. So when you get to this point, in this case, for instance, you see that here, you cannot go on further to do a Gaussian elimination, apply the Gaussian elimination techniques. So the idea is that if you can change the row, right, then you can continue. So if this was a very big matrix, then just because we are unable to change, we are unable to proceed. So let me just say, if this was a big matrix like 1, 2, 3, 4, and then maybe we have 0, 0, 3, 2, 1, 3, 2, 0, 0, 1, 3, 4, something like that. The Gaussian elimination process, once you have this, okay, then you have a big challenge. Let me even put 0 here so that it makes it like we have escaped the first step. But the Gaussian elimination process is such that once you have this type of matrix, you are unable to proceed. Why? Because you need to now, the method says now make this 0 using the scalar here, right? Make this 0, but you cannot make this 0 because you have to divide by 0. And that is the main problem with the Gaussian elimination technique in this direct sense. So the idea is that, okay, in such a situation, when you have a 0 on the diagonal that you now need to also use that diagonal, because the Gaussian elimination, all that we are doing is, for instance, in this case, we will say that row 2, right? If you want to do the elimination, we say row 2, then take row 2 minus, it's row 3. We want to change row 3, right? Take row 3 minus a scalar, right, of row 2. So what will you do? This scalar here, if you just say, okay, what scalar can you take such that you can write this 3 here to be 0? Do you understand? So you take row 3, then you say you need a scalar, this scalar m here, which is just nothing else, but it's supposed to be the diagonal of the previous row, right? So in this case, this is 0. And then the element you are looking for. So this one, right? This is 3. So that's the scalar you need. And this scalar here, you cannot use. So the idea is that, okay, let's row exchange. Let's do a row exchange. In that sense, you can do 1, 3, 4. Then you can exchange these 2 rows, right? Then you can have 0, 3, 2, 0. And then you have 0, 0, 3, 2. And then you have 0, 1, 3, 4. Okay. So in that sense, now we are able to still have something on the diagonal entry, which is what we want for our L. We want some element on the diagonal entry, not zeros. If there's a 0 going to be on the diagonal entry for the upper triangular matrix, then we are in a problem. So we do this row exchange, and then now the matrix looks like this. Okay, so here again, all that we have to do again is do another row exchange. Then this one comes up, this one goes down again. Because again, now if we want to do R4, right? If we want to do R4, we see that there's an element here, but we don't need any element here. Here, so in essence, when you do your Gaussian elimination, you expect that at the end, you have entries only in the upper part. And then in all the elements under the diagonal should be 0 entries. This is what you expect. So you expect that all there are entries from the diagonal up, and then all the other entries below the diagonal are all 0 entries. So in this case, you see that we still have these entries here. So we have to still do another row exchange. So if we do that row exchange, then this one goes to 1, sorry. Then this guy goes to 1, this guy goes to 3, this guy goes to 4. The 2 comes here, the 3 is there, and then this one goes to 0. So already then, this gives us a good way to then do furthermore, apply the Gaussian elimination technique, such that now we can take this guy to 0. So that is how the whole this idea of the pivoting comes in. I don't know if it makes sense now. So this is the whole idea of how this pivoting works. Okay, and then as I said, this whole pivoting thing, because I gave some properties of this permutation matrix, right?
Please, can I ask question? Want to go the next slide? Yes, because we have AX equals to B. Now we are only dealing with A matrix A. What about the right hand side? Are you also
Yes, exactly. So that's what I'm saying. That all the permutation matrices that you are using, right? So exactly in the example that I gave here, if you solve this and then in the right hand side you do not multiply by the permutation matrices you are using, you will solve a different problems, because you have exchanged 2 rows. If you do not keep track of those exchanges, if you do not keep track of those exchanges, then in the end you realize that, so what happens is all the permutation matrices you are using. So here, first one, we call it, let's call the first permutation matrix we have used in this case, for instance, sorry. Okay, so here we have used a permutation matrix that has exchanged this row, only the row 3 and row 4, right? We have done row 3 and row 4, row 2 and row 3 exchange. And then as well here, we have done a row 3 and a row 4 exchange. So if you have a 4 by 4 where you have done a row 3 and a row 4 exchange, a row 2 and a row 3 exchange, then you know that your permutation matrix will be nothing else but this guy, right? Where it is the identity matrix, but now row 2 and row 3 are exchanged. So we call this, let's call this P1, because this is what we used to do this first row exchange. Then the second row, the second exchange here as well, where we exchange row 3 and row 4, we have used another permutation matrix. Let's call it P2. Now that permutation matrix will be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Because now in this permutation matrix, we have exchanged row 3 and row 4 from the identity element. And here we have exchanged row 2 and row 3 from the identity element. So this is the second permutation matrix that we have used. Do you understand? So in the end, what we have to do, or what we will do is, we'll take our permutation matrices P1, okay, because we'll take this one, which gave us this exchange. We'll take this guy, which gives us this exchange. And all the permutation matrices we have used, we are going to keep track of them. And then we are going to multiply them, because in the end, when we do PA, it's all the permutation matrices that we have used times A. I don't know if this makes sense. And then on the right-hand side, we use that same permutation matrix for B. So in the end, you have to, you'll be solving a system of PA is equal, or PAX is equal to PB. Because if you do a row exchange here, and you do not, if you do a row exchange on the left-hand side here, and you do not do the same row exchange correspondingly to the right-hand side, then you are not solving the same system. So basically, all that you are saying is you have x1 plus 2x2, very simple, and you have minus 2x1 plus 3x2 is equal to 3 and minus 2. If you do a row exchange, for instance, on the right-hand side, then you are saying that it's minus 2x1 plus 3x2 is equal to minus. But let me just not talk about the right-hand side. Right? And then you have done a row exchange, so you have x1 plus 2x2. If you do not do the same row exchange on the right, then you are going to do this, right? And this is not this equation, this system here is not the same as this system. It's a different system. The only way this system here, okay, let's call this A and let's call this B. The only way, if you do a row exchange on the right, on the left, and you come here to B, then you must do a corresponding row exchange on the right, such that now it gives you also the same thing on the right, right? Then you have minus 2 and 3. In that case, then you say that you are solving the same system, or the same system. Just now you have changed the rows. So if you do the row exchange, and this is why I kept saying, if you do the row exchange, even here, right? If you do a row exchange in this case, if you do a row exchange here, then you must do a similar one on the right, because if you do not do that, then you are solving a different system. And this is why in the exercise, you see that when you solve the right-hand side the one, even for example, John, your work. You just did the pivoting on the left hand side of the system, and then you didn't do anything on the right hand side. So in the end, you have changed the system on the left, but you have not changed it accordingly on the right, and you do not get the same solution. I hope this is clear.
Yeah.
It's clear now.
Yeah.
Okay.
It's clear. If you can
Maybe.
Example.
Can I? Okay, you can talk.
I'm not hearing.
Okay.
I was saying it's clear now, but if you can take examples, we say to simple example too.
Yeah. So we'll talk about example later. So now let's go on. I want to talk about yeah.
Maybe another thing, yeah. If we have if we have that 4x4 matrix,
yes,
and then I change row 2, I carry this row in the previous, yes. What if on the previous page? Yeah, there. Here now you moved this here. What if I want to just move this directly up to down there? I want to exchange row 1, row 2, and the 4.
Yeah, you can do that. You can do that as well.
And I will have one permutation matrix, yeah?
Exactly.
Okay.
Exactly. So you can go from here, and then all you can do is 1, 2, 3, 4, and then you bring the whole of the 4, 1, 0, 1, 3, 4, right? And then you can even bring this guy as well, 0, 3, 2, 0, and then you bring this one 0, 0, 3, 2, something like that.
Yeah, that's what I wanted.
Yeah, and then you should know which permutation matrix you are applying. So here, what have you done? You have left this guy. You have changed what?
That one for the last
4,
one.
right? So row 4 is here.
Yes.
And then row what?
That one was left.
That one was left. And then this one was there.
Okay.
So this is the permutation matrix you have used. Okay. So basically, all that I'm saying is that if you multiply this guy here by this, right, it should give you this, right?
Yeah.
If you take your P and then you multiply, let's call this matrix Q, and you multiply by Q, you should get this matrix here. So this permutation matrix you have used, you must, in the end, keep track of all of them and multiply them also to the right-hand side. Because then it helps you know that, okay, you use P1, P2, P3, and so on up to Pn of A, and then you can do the same P1, P2, or the same up to Pn times B. Then you now solve this PAX, right? PAX of PB. And when you solve this, so it's going to be PLU of X of PB, and then you'll be able to solve it again in the same machinery that we've been using over and over again, right?
Now, in this case, this L you're using, is it the one which is equal to PL or?
I don't understand.
Like when we change the other.
So if you do your, if you do your LU decomposition, right? If you do your LU decomposition, then all that you do is that you have your A is equal to LU. But if you have used a permutation matrix, then all we are saying is that all the permutation matrix that you have used, you can still use this as well. Write it as this.
Okay.
Because in the end, whatever happens, in the end, if you solve this again, right? If you do a further Gaussian elimination, you go again to a U, an upper triangle. I mean, maybe we can continue with it. Sorry, I was just thinking this was some undergraduate Gaussian elimination thing. So let me try. Let's go back. Okay, let's take this one here. Okay, let's take this one. Right? Can you see this one?
Yeah.
Now let's go on to the next stage. Okay. So let's go on to the next stage. So let me write 1, 2, 3, 4. Just for you to see, then 0, 1, 3, 4, 0, 3, 2, 0, 0, 3, 2. 0, 1, 3, 4, 0, what? 3, 2, 0, 3, 2, 0, 0, 0, 3, 2. Something like this.
Please, can you also add the right hand side at the same time? Then
No. But I'm not adding right hand side. If you are doing the composition, take your matrix A. If you add right hand side to it, you are lost. You get confused. I know that sometimes people do this. People do this, right? And then if there's a right hand side, maybe if there's a right hand side that we started with. Okay, here I didn't write any right hand side, but let's say if we started with some right hand side, 1 minus 1, 0, 3, right? Then already here, we would have already exchanged, what? Row 4 and row 2, right? So if we took a certain right hand side like this one, then it means we already have exchanged this 2, right? Mukaila, this is what you are saying. 1,
yes, please.
3, 0 minus 1. 3, 0 minus 1. This is what you are saying, right?
Yes, please.
Yeah, so I mean, people also like to do use this technique as well, just to do the Gaussian elimination. But the reason why I don't do this is because in this course, we are thinking of the implementation as well. It's not just the analytical solution. So we think of solving it, but not just because if you have to implement it, how are you going to add this part to your implementation, right? So you must think of how to, we are thinking of the implementation as well. That's why I'm just using the matrices themselves. Because in the end, when I want to implement it, I'm going to talk about the matrices and the vectors. If I do this, then I cannot tell how I'm going to implement this in that sense. That's why I usually do not add this aspect to it. But please, do you understand?
Please.
Yeah, but if you do that, if you add this part to it, then it gives you the understanding of maybe the analyticals, how you are doing what you are doing analytically. But it does not help you to understand how the permutation matrices are going to be used on the right-hand side. So let's just take this part, the A, and this is the B, this is the A, right?
Okay.
If we now want to go on further, then we will say that we'll have 1, 2, 3, 4, 0, 1, 3, 4. Then now what we want to do in this case, okay, in this case is to take this 3 to 0, right? So we multiply. So let's take row 3. Row 3 times what? Row 3 will now be row 3 minus 3 row 2, right? So if we do that, then we have 0 here. Then 2 minus 9, which will be minus 7. And here we have 0 minus 4, which will be minus 12. Then the next row, right? Then the next row is 0, 0, 3, 2. So of course, what then we'll also do is that next we'll take, because the next one is take this guy to be 0. So how do we do that? So you say row 4 is equal to row 4 minus, let me say what, or let me say 7 times row 4 minus 3 times, so 3 over 7 row 3. Let me say plus, right? So if we do that, then we have 1, 2, 3, 4, 0, 1, 3, 4, 0, 0, 0 minus 7 minus 12. Then we have 0, 0, 0, right? Then we have 2 minus 2 minus 3 times 12, 36 over 7, right? I hope I'm correct. 2 minus 36 over 7. So this will be minus 3 point something, right? Minus 3 point something. Let me say 2. So this is the matrix, the upper. This name becomes your U, right? And then the lower we said consists of all these scalars that we have used. This guy. So we use those ones to create the lower matrix. So in this case, we have a U, which is 1, 2, 3, 4, zeros here, blah, 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 up to minus 3 point, something like this. This U here. And then your L, right, is 1, 1, 1, 1, zeros on the top. And then if we go back, okay, so we just did the L is, what are the L's that the scalars are used? We did the change here. Okay, so we did this one, right, for this guy, and then we did R4. So we can go and say, okay, how was it? This one. So we have this guy. Let me write them out. You see, 0, 0, 0, 0, 0, 0.
So in that case, we multiply it by -3. Why do you write +3 here?
Where? No, I'm not done. I'm writing it out clearly. Okay.
Like
So
the scalar multiplication, it was -3.
Yes. So this one.
Negative, yeah, it was -3. So what do we write there in the lower matrix?
This is row 3, column 2. Yeah. So you write 3. Of course, in some books they use the negative, right? They use the
But what is
negative of the
right?
scalar.
So what shall we use here?
Yeah. So here we come. We've written this one. That was the only scalar we put there, right? So this is the matrix we start with. We just do a rows exchange. Then we came to this guy, and then we use this guy, these two. So 1 was here, 3/7. I'll put zeros for the rest. Maybe I put negative.
I think it's the 3/7 should be negative, but the 3 is positive because we
Yeah.
are multiplying 3 by.
No, that's this. So this is negative. So it's correct.
Why?
The 3 on 7 was, yeah, 3 on 7 was negative. We already multiplied by negative. That's why it's tend to be positive. It's like rule 4 minus bracket will be -3 on
Look,
7 to 3.
here
That's
is minus here.
It's minus here.
Here is plus.
So
Minus here, plus here.
So I expect the minus on 3.
Yeah, this is
And
exactly what I'm
3/7
saying. In some of the books, they have minus A, J, I, A, I. So if you do the minus here, then you do the plus here. If you put a minus here, then you put a plus here.
That is okay.
So now you have your L and your U, and then you have a P. And then we have a P. The P we did in the first instance was this one. This was the P.
Yeah.
So you have your P, you have your L, you have your U, you have your X. Then you take the P and the B. Then you can solve again your system, right?
Okay.
Do you understand?
Yeah.
Yeah, so this is how the pivoting is done.
So what will be the Y?
You said?
What will our Y be now? Shall we have to solve PLY equals to PB first?
So we have
PLY,
what?
PLY equals to PB. PLY.
So you have PAX, right? And then you have is equal to PB. Your PA you can write as PLU. Okay.
Please, sir.
You can write. No, you write. Sorry. I don't need a P here. Okay.
Okay.
Sorry, I don't need a P there. Also, yeah, this here I need a P.
So that means that the L that is obtained there was a multiplication.
PAX. Is that?
Okay. That is okay.
Okay. So now the A is then, sorry, so this is the right, is the inverse of LU. This is the A now. So for your AX is equal to B, your A now is this guy, LU of X.
I was thinking
Yes.
that since our AX is equal to AX is equal to maybe is equal to B, this. And we have said that our now our real L that we need is equal to the P times what? Times now the L that we have that we would have obtained.
I don't understand. So if we go back, I think that was a little mistake that I did. P
Like what?
is equal to PB. Right? So if we take this part, your PA is equal to your LU. And your
Now,
A is equal to P inverse of LU.
My question is, which L are we using here?
Which
is it
L?
the one which has been replaced by P? Oh.
No. You are using this L. The L you have obtained after your process. This is your U, and then this is your L. And then this is your P. This is the P we use, right? Please, do you understand?
Yeah.
So we are saying that if you take your PA is equal to your PAX is equal to PB, because you need to multiply the right-hand side by the P, the same permutation matrix. Then you can write your PA is equal to your LU that you now have, okay? Your PA is equal to your LU. So your A is equal to P inverse of LU. And that means that your AX, right, is equal to this A here that you now have. You are going to put there as your P inverse LU and now solve this, right? If you solve this, then you can solve the right-hand side. So for the right-hand side, if you multiply, let's just say, if you do the right-hand side, right? We have PA is equal to our LU, and then right-hand side, we have PB. So we have now A is equal to P inverse of the same. This, and then here we have PB. So let me call this B tilde, something like this. So again, you can go through the same process. Let UX is equal to Y, right? And then let B inverse of L of Y is equal to B tilde. And then you solve for X. You solve here first, and then go back and then solve second, backward. So this is the whole idea of the permutation matrix.
Please, sir.
Yeah.
I think that it is equal to B because we just replaced the expression of A in the expression. The second line. I think that it is equal to B because A is equal to P minus 1. The inverse of P times L times U.
Is it A is equal
to P minus 1 LU.
Yeah.
So it is like we just replace the value, the expression of P of A in this line. So normally we should get P instead of A with something.
We should get can you can circle where you are talking. Just circle out what you're saying.
Yeah.
Yes.
I think that is B. Not there is no distinction.
You are saying that it's just the B, not the permutation matrix.
Yeah, yeah. Because A is equal to all this. So it is like we just replace the expression of A here.
Maybe I've understood it. I don't know whether I can say something.
Yeah, you said I'm listening.
I was answering Ezekiel.
If you do, you're saying is P LU is equal to B. Sorry, X.
Yeah.
No.
So if you do that, if we go back, so this is why I kept saying that if you go back, so even if then for the normal Gaussian elimination, where you add everything, do you get it?
Yes.
If you do a row exchange, in this case, this row exchange, if you do a row exchange here, you change the right-hand side. Do you understand?
Yes, but I did it yesterday with for the exercise you gave us, and I found the answer.
You did what?
Yeah, I did it yesterday for according the exercise that you gave us, and I got the answer.
And you got the answer without doing any exchange on the right.
Yeah, exactly.
But how did you get the answer? So what answer did you get?
I P L S is equal to P. No, sorry. L U S is equal to P B.
LUX is equal to PB.
L S equal to P B. That is what I did.
From yesterday.
Yeah.
Prof. Hello?
Yeah, I'm listening.
Yeah, I think maybe you make a new page. Here, okay. According to what you got, as what I'm understanding, is that let me get an annotation here. He is saying that L U X is equal to PB. Now, the L that is using and the U are the ones of the matrix that has been exchanged. Yeah. If that is the case, then he's right. Because you told us that if we have X and it is equal to B, then if we work out on this one, we end up exchanging the rows for this, then it would mean that we're going to have, if we want the real A, if we need now the real L that we always wanted before, it means that it would be now P times the L. So I think this is here is right if it is using this L here, not this one. Have I successfully confused him or he has understood?
So let me go back. If you do the pivoting technique, then your PA is to LU.
Yes, that's right.
Okay.
P is equals L. Yeah.
Then if you have,
it's easy to derive.
If you have PAX
is equals to P.
Then
P
you can write
PB.
PB.
Yeah.
Okay. And all we're saying is that if you let U of X to Y
is called P.
then LY is equal to PB.
Here we directly to put PA is already LU, so LUX is equals to PB. Once if we have.
So Dejan, you said you did P LU of X is equal to B, right?
That is okay.
Yeah. Yes. In other words, that's it. Yeah.
Okay.
If you can multiply both sides by P, then in other words, LUX equals to PB. Pre-multiply both sides by P. Just
yes.
Right.
Yes.
Yeah.
Okay.
We shall understand more by doing problems.
Okay.
Yeah, I'll give you more problems to do. So in the case, so this was okay. So maybe this is a bit exercise that we did. Okay, I don't understand what you're saying. If we do this, I think that's what you. Okay. So if we do pivoting on both sides, okay. So as I said, pivoting we can do three, but if we do a post, right? Also, then we do the same technique of PAQ. That's we call the total pivoting. Okay. Then you can have PAQ equal to LU, and in that case, of your AX equal to B, so you can write PAQ. And then you can do U inverse of X is equal to PB, where now you have this as your LU and this as your X. So we call it S star. In the same way now, you can do Y equal to PB and U equal to Y equal to Q. So this is a case where you do pivoting both to the left and to so this is total pivoting. So total pivoting means you do pivoting, you do row and column. Okay. And of course, also in MATLAB, you can do the same. So also in MATLAB, you do L, U, L, and you do LU of your matrix, and it gives you all this, this U, and then your P, your Q, your L, and your U. So this is for MATLAB. So you can go and check if we have A to be 1, 2, 3, 4, 0, 1, 3, 4, 1, 0, 1, 0, 2, 5, 4, 5, 0, 6. And then we do an LU PQ LUPQ. Okay, so in MATLAB, so let me do a sparse matrix. Maybe this will be better. Okay, so if we do then LUPQ of W, oh, what is that? Okay. Maybe I need more. Okay. So if you go through MATLAB, you can try where you create. Yeah, I decided to create a matrix of size 8 by 12, and then just do the LU decomposition. But maybe I think if I create, so this is 8 by 12. So maybe if I create, this is for W, so W is 8 by 12.
What is the meaning of SPW? SB
So it's just a sparse, it's a sparse diagonal matrix. So this one is 8 by 12. I want to make it a 12 by 12. So 8.
Okay.
I can add 4 more, right? I can add 4 more. Okay. Let me see if it will still work. Okay. If not, then just do the spy. I'll explain some of the commands now. So spy. Can you see the diagram?
Mm.
Can you see the diagram?
Yes.
Okay. So if you do spy, then if you do the MATLAB command, it shows you the metrics, how the matrix looks like. All the non-zero, it shows you all the non-zero points in the matrix.
It does what?
Right? All the non-zero points in the matrix.
Mm.
So for instance, if we take W, if we take the first column, you see that we have non-zero point here, non-zero point here, non-zero point here. And you can see the corresponding non-zero points. If we go to the second column, you see our non-zero point, non-zero point, non-zero point, non-zero point, non-zero points. You see the same pattern in the spy, right? So this one gives us an idea of how the matrix looks like. Visualization of metrics, right? Just for you to visualize how the matrix looks like. Okay, but what I was trying to do, but which I need, I'll need some, because I need to create a bigger matrix for that. Was to show you this thing about how to do the LUPQ when you have a total pivoting method. Okay, so you have a total pivoting, how that you can also do a total pivoting MATLAB, exactly as I explained in the example. Not the example, exactly as I explained here. That when you have a total pivoting, then now you have a row and a column. You have a row and a column exchange. But in MATLAB, this command you use for the total pivoting is when your matrix A It's a sparse diagonal matrix, right? Sparse diagonal matrix. So of course, I'll show you over time how to create sparse matrices as well in the MATLAB. Okay, so I'll go on to method. I'll go on to another method. But maybe before that, as I said, I wanted to show you this idea of the sparse diagonal matrix before. So for instance, in MATLAB, let's go to MATLAB again. In MATLAB, you can create ones, a vector of ones, only one. You can do A is equal to 2 times B. Now we have A is now a vector of only B, only 2. We can do 3 times B as well. And then now I can create a new matrix, the sparse diagonal matrix. That is going to be my B, A, and C. And then I say that -1, I will explain to 1, and then 10 to 10. And then we'll see this new matrix that we have created, T. I hope yes, this is the new matrix T. And then now I can do a spy, because this is better for you to see, a spy of T. Okay, so you see that I've created this, you can see the diagram as well, right? If I type T on the command, it gives me only some entries, right? Only entries where I have only the non-zero entries. Shows me only non-zero entries. Only non-zero entries, right? So how did we, what does it mean by this T? So this T, we are saying that we are creating a sparse diagonal matrix, right? It's a tri-diagonal matrix. So let me annotate. So we have created a T, which is 10 by 10 matrix. We have created, so here, sparse diagonal means that where this B is, means that we have 2 on the main diagonal, one on the sub-diagonal, and 3 on the super diagonal. Diagonal. So this means that we have a matrix where we have 2 on the main diagonal, and then we have 1 on the sub-diagonal. Everything here is 0, and then here we have 3, and everything here is 0. So this is the matrix that we have created, and this is how we have created this matrix. So this is a sparse, this is an example of how to create a sparse matrix in MATLAB. And then the SP diagonal here just means a sparse diagonal matrix. And in that case, it means when you write the SP, immediately MATLAB starts saving, MATLAB starts doing everything in a sparse setting. Sparse setting means it doesn't save all the matrices, all the entries of the matrix. It only saves the non-zero entries of the matrix. Only the non-zero entries of the matrix. So it gives you the column, the rows, and the column order. So here, example, if you come here, it tells you one column one is 2, two column 1 is 1. This is exactly what I've done here. Right? This row 1 column 2 is 3, row 2 column 2 is 2, row 3 column 2 is 1. So exactly you can see what I've done, I've written here. This is exactly what it's doing. So every other entry which is 0, it does not save it. It does not store the values or those values in its storage setting. Okay. So any questions? Now you have created a tri-diagonal matrix. So next, I'll explain what we call the QR factorization algorithm, which is the next algorithm method that I want to discuss. Any question so far?
No, from here, no.
Okay. So at least you have understood the sparse, all this thing about sparse. But it's only the non-zero entries that are being saved. The rest, we do not save them. Okay. Then we go back to our board. So I think to start that, last time we started with simple definitions of certain things that we need to know about some special type of matrices. And one of them that I spoke about diagonal matrix diagonally dominant. Then we say that absolute value of the diagonal greater than the absolute value Okay, so so that this holds for each I 1, 2, then what you should know, very important theorem, is that if we have A to be, let me call this strictly diagonally dominant. If we have A to be strictly diagonally dominant, and it is not singular, okay? So if we have a strictly diagonally dominant, it is also not singular. And then the Gaussian element can be performed, right? On AX or to B. To obtain solution. Without row or column interchange. Okay, so if we have a strictly diagonal dominant matrix, we know that it is singular, and then we can also do Gaussian elimination, and we are sure we will not need a row exchange or column exchange. So it's also good criteria to know if you are going to do, if the system you are going to solve requires a row or column exchange. You can use the idea of the strictly diagonal dominance to check if you need this. Okay, and then there's a whole proof for it, but I'm not going to address or talk about this proof. The next one that I want to talk about is what we call.
Excuse me, Doctor.
Yes. Yeah.
That is strictly dominant, diagonal dominance.
Yes. Yes.
Is it the same thing as the matrix being positive definite?
Now I talk about.
Okay.
Matrix is positive definite. Positive definite. If it is symmetric, if it is symmetric and X transpose A of X is greater than 0 for every vector X which is not equal to 0. So this is positive definite. Of course, another important thing is that if you have A to be an n by n positive definite PE matrix, few things. A is non-singular. 2, the diagonals are all positive for I 1 to n. 3, the maximum entries are all less than the maximum entries on the I1 to n, then 1 less than equal to k, and then 4, the square of the entry is less than the product of aij, aii, and ajj, where I is not equal to j. So if you have a positive definite matrix, which is symmetric, if it is symmetric and this condition here is satisfied, then we say that the matrix is non-singular, entries on the diagonal are positive, then the maximum entries on the diagonal are all greater than the maximum entries on all the other elements, on all the other all other elements on the row, and then the square of the entries of the matrix which are not on the diagonal are less than the product of the entries on the other aspects of the matrix. Of course, there are other definitions. Another definition, maybe definition 3, is what we mean by a leading principal submatrix. So if we have a matrix A, which is Rn by n, then we say that a leading principal matrix of A is of the form, let me call it AK, A11, A12, A1K, A21, AK1, AKK. For 1 less than K less than N, and then an important term of this is that if you have a symmetric matrix, A is positive definite if and only if its leading principal submatrices has positive determinant. So, example is that if you have a matrix A and you have 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2, we know that 1 A is symmetric. Then what is the leading principal submatrix? So the determinant, we said the determinant is positive. So we create A1. Let me write it. A1, okay, is 2. So the determinant of A1 is 2. A2 is 2 minus 1, minus 1, 2. And the determinant of A2 is 4 minus 1, which is 3 greater than 7. And A3 is the matrix itself. And the determinant of A3 we can also see is equal to 4, which is positive. So how are we creating this A1, A2, A3? So A1 is this guy, A2 is this guy, and then A3 is the whole matrix. So you take, if you have an AN by N, then your leading principal matrix of A is of the form this, where your K is less or equal to N. Right, so in some sense, you are taking a matrix A, which is K by K. And K can be equal to N as well. So this is how to determine, and then as the theorem we just said, that if you have a symmetric metric, we say that it's positive definite if its leading principal submatrices has a positive determinant. Then we know that if we have a symmetric matrix which is positive definite, as we said in the earlier in the other theorem, right? That if you have a strictly diagonally dominant matrix which is non-singular, then Gaussian elimination, you can do Gaussian elimination and get a unique solution without doing any row or column interchange. So in that sense, if you do also have a symmetric matrix which is positive definite, and the leading principal submatrices have a positive determinant, then the same principle we can also talk of again, that if we have a symmetric matrix which is positive definite, if and only if the Gaussian elimination without row exchange can be performed. Right, so this is a very quick theorem that I'm saying that if A, write it, then a symmetric matrix is positive definite, right? It's positive definite if and only if Gaussian elimination without row interchange can be performed. On the system, the linear system AX is equal to B. With all pivots elements being positive. Okay, so I want to take a break here, and then I'll get some water. So first, you must not forget. So if I give you a matrix, you must be able to check if it is symmetric positive definite. Maybe one other thing I forgot was to talk about semi-definite. Semi-definite. So let me add it here. So this is for symmetric positive definites. If on the other hand, we have X transpose AX is greater or equal to 0, we call it semi-definite. So that's the little information that I skipped. So in MATLAB, you can do Cholesky of A, and then you get Cholesky. You get the Cholesky algorithm implemented as well. So let's take an example of a matrix. Let's see if we can do Cholesky's to it. So let me type a matrix. I think we did an example already. We had A, which was equal to 2 minus 1, 0. And then we had K, symmetric. Then we had 0, minus 1, 2.
Sorry, Professor, we didn't see.
Okay, I share my MATLAB screen
Okay.
now. So if we have such a matrix, we know that it is symmetric, right? And it is also positive definite because we checked already that we can use the determinants, the leading principal matrices. If they have all positive, if they are all positive determinants, then we can say that the matrices as well. Then we can say that the matrices as well. What do we say? If we say that, we can say that the matrix as well positive definite. Okay, so we have this. Then we can do R is equal to Cholesky of A, and then it gives us the R, right? So if we annotate it, basically what have we done? We have done that A is equal to R transpose R. And then MATLAB says that if you have an A, if you have an which is 2 minus 1, 0. So we have 2 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. We have been able to split this into an R. We said that R is upper triangular, which is square root of 2 minus square root of 2 over 2 of 0. This is 0, 0. And then this is square root of 2 something, okay? This is 0. This is another number here, another. So it gives us something like this. And this is basically using the method that which I just described earlier. So if we go back and want to even test the method, okay, so let me clear annotation, and then let me go back to here. So if we have a matrix A, which is 2 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. We are saying that we can do Cholesky's. If we take the diagonal first, for instance, we can do the first entry of the diagonal. So our R will just be square root of 2. Then for the other entries, if we follow this guy here, so here basically all we are doing is we expand this matrix, we equate to A. We know the values in A. So to find the R's, so for instance, if we equate this to A, and A is 2 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. Then we know that this value here corresponds to this one, right? So our R11 squared is equal to 2. And this will give us R11 to be square root of 2. Then the next step is that if we know R11, then we can find R12. So R12 will just be, we equate it to the other side, which is minus 1 over R11, right? So this will not be nothing else but 1 over square root of 2. So then R12 we know is square root 1 over minus 1 over square root of 2. So this is how we same as what I just wrote, and so on. Once you have your R, it is enough, and then go down all that Cholesky requires. You just need your R, because then the matrix is R transpose of R. So if you are given an AX, we can substitute your A, and then you solve for X. Also by back substitution, forward substitution. With any question about Cholesky? Okay, if there's no question about Cholesky, then I go to the next direct method. Method 3. Okay. So the K-1 factorization really starts with we try to apply the complete process. We try to apply the complete process. So let me go down and check for you. Okay. So probably I'll start with an example, and then to see we- so for QR factorization, it's a very popular method. It's also a method, usually one of the methods also for finding eigenvalues, approximating eigenvalues. So this is a method that I'd like to treat because then it covers as well some other aspects of the numerical the eigenvalue problems that we solve numerically. We'll borrow some of the ideas from here. So this is one of the methods that I usually like to treat as well. so that you understand the case. So usually, so we apply Gauss-Schmidt process in this way. So all we are doing is we have an A, we want to split it into Q and an R such that our Q, which is oh sorry, let me write. So we have an A, is an N, okay. N by N matrix. We have an M by N matrix, and it could be M is greater or equal to N. So it doesn't have to be symmetric. It doesn't have to be a rectangle or a square. We just need an M by N matrix. And we say that we can split this M by N matrix into a QR, where Q is an M by N, it's an orthogonal matrix. By orthogonal, I mean Q transpose over Q to give us identity, while R is an M by N is a rectangular. So the Q is a square matrix and the R is a rectangular matrix. Whose entries below the main are equal to 0. Whereas its diagonal entries
Doctor,
yeah,
I thought, I think our Q, the orthogonal matrix,
yeah,
has the dimension similar to that.
has what?
A.
I can't hear you. You said that I mentioned
Yeah.
what?
What I'm saying.
Yeah,
Hello?
I'm listening.
The orthogonal matrix Q
Yeah,
has the dimension as A, whereas the R is gonna be a square matrix N by N. I don't know. Is that true?
Q is
Q has a similar dimension like A.
I mean, R has a similar. Q
So
has
I expect this to be N.
No, it's M.
So Q has a similar dimension with it has, I mean, it is R which has the similar dimension.
Q is a square matrix.
Okay.
And R is a rectangular matrix.
Okay. Okay. Thank you. Thank you.
I mean, it depends on how you write. It depends on how you write your metrics. So in this case, if you put Q to be M by N, then you have to put R to be N by N. This is matrix computation, right?
Okay. Okay.
So you have to be careful. If you say M is less than or equal to N, then you can write it in what you are saying. So that's all you have to be careful about. Please, is it clear? So in essence, let me save this one because I'll start again. In essence, we have a matrix A. Let me draw. We have an M. So this is geometric. By N A, which you say can be written as an M, right? An M by M and an R, which is an N by N. Sorry, an M by. So this is how you have to picture it. And of course, if we can write A to be QR, then we can write AX. If we have AX is equal to B, let me just not. Let me just. Yeah, if we have an AX is equal to B, then we can write QR of X is equal to B, and X will be nothing else but QR inverse of B. And this will be nothing but, because you cannot find the inverse of R, you have to be careful. So you have to write it. Let me not write it wrong. So you can have Rx equal to Q inverse of B. Of course, if it is orthogonal, then it's the same as this. And then X will be equal to R I don't know if I should write this guy. Q transpose B. This is a bit tricky. Okay. So um, so in essence, you can write your did I write Taylor algorithm? Let me write it out. Okay, so what we do then is to, let me see. There's a small error in the lecture notes that I'm seeing. Okay, I think there's an error that I'm seeing. Okay, so maybe what I'll do is that I'll go straight then from here, I'll try to go straight to iterative methods. But when we start the eigenvalues, I'll address again the QR problem again. So let's go to iterative so that you have an idea of iterative methods now. come back to the QR algorithm when we come to eigenvalue problems again. Okay, so iterative methods, as I said, the main bottleneck or the main idea around iterative methods is what we call, or what we popularly call, a fixed point. Fixed point. So fixed point methods, that x one t of xf. And this is exactly how we try to write our iterative methods as well. So we try to write iterative methods kind of like fixed point methods. And then we use what we know from fixed point ideas to solve the same bits again. So that I'll talk about certain important things like because we need a definition of a norm. This you need the definition of a norm. So if we have a vector norm on Rn, the function from Rn to R, such that we have four, maybe three, let's say four. The norm is positive for x, and then it is 0 if and only if x is 0. 3 scalar x will give us this for all alpha and alpha, and x to and I will x plus 1 is very simple, plus 1 for all x and y. So this is the definition of a norm. Then I'll talk about the particular norms. We have the L2, definition norms for vector. For vector x.
Look, please, I think someone is joining again, so he wants you to accept him.
Okay. Sorry. I think I have set it to automatic joining.
I think he has joined now.
Okay, good. All right, so we have if we have the norm, we have the L2 and L infinity norms. That's what I want to talk about. That's what we'll be addressing in most cases in this lecture. I define them by 2, which is equal to the sum I1 to n of xi squared. And then we have infinity norm, which is the maximum value of xi of every entry. And so, of course, this norm is popularly called the Euclidean norm. I'm sure you all know about it. Okay. So, popular thing to know is a theorem called the Cauchy-Bunyakovsky's. I mean, people call it inequality. Is that for each x, which is x1 to xn, so and so, and y, which is y1 to yn, so on so, in Rn, x transpose of y is written as the sum xiyi is less than the individual sums I1 to n, I1 to n. This is square roots, this is square roots, and this is the same as x and y. So this is a very popular theorem. Everybody in mathematics needs to learn how to know how to prove it. Of course, so if we have set definition for the norm, then it's possible for us to find the differences as well. So the definition, another definition is that if you have x, which is a vector x to xn, and y, which is another vector y to yn, let me say layout transpose. The L2 norm, the L2 and L infinity distances between x and y are defined. So if you have two vectors and you want to find their L2 distance, then we say that take the sum. Let me put it. Take take the sum xi minus yi squared I1 to n square root. And then the L infinity will be nothing else than xi1 I1 and the same. Okay, so if you want to find the distance between of two vectors in L2 or in L infinity, well, this is how you do it. Other definitions, if you have a sequence xk, k from 1 to infinity. Let me write it. Of vectors, you have a sequence of vectors in Rn. is set to converge to X with respect to the norm with respect to infinity if and only if the limit is equal to infinity of X I of K is equal to Xi for each 1, 2, and no, sorry, I think I mixed a theorem. Is that to convert to X with respect to the norm? I think I missed. Is that to convert to X? If given epsilon that exists an integer such that Sk minus X less than epsilon for K convergence. Okay. Then there's a popular theorem that says that if a sequence K1 to infinity converges in Rn with respect to L infinity if the limit K to infinity Xi is equal to Xi for each I 1, 2, then quality of the theorem. This is the quality of the norm. So for each X in Rn, the quality of the norms means L2 norm and L infinity norm are equal to a certain scale. You can write X.
Please, will you be sending this slide to us maybe after the class?
Yes. All of it, you have it. Before the PDF I'm writing, you have it as well. But this slide as well, I'll send it just like I did last week.
Okay, so
Yeah, just like I did on Tuesday. So here as well, if you have a sequence that converges to X of Rn, and with respect to the infinity norm, if the limit of that sequence converges to an Xi for each I in for 1 to n. And then this is the equality. This theorem talks about the equality of the norms. It means that our L infinity norm is related to our L2 norm, the Euclidean norm, in this sense, by a scalar square root of L above, is bounded above by square root of L. Then we can extend the same idea, of course, to matrices as well. It means we can define the matrix norm, right? The same thing, we can define the matrix norm, which means that we should satisfy 4 properties, maybe even now 5. Then it should also be, can find the distance between 2 matrices of the same dimension. So on and so forth. So, because I'll not be able to address every issue on this. So the next one is to talk about iterative methods. So if you consider a matrix, the iterative method is like that. So exactly as I've written so far. So an iterative method to solve the n by n linear system AX is equal to B starts with an initial approximation x naught to the solution of and then generates a sequence. So that's why sequences. Generates a sequence of vectors x of k1 to infinity, or k0 to infinity, that converges to x. So we say that iterative methods technique involves a process that converts the system AX is equal to B into an equivalent system of the form X is equal to TX plus C. For some fixed matrix C and vector C. So after the initial vector x of 0 is selected, the sequence approximate solution vector is generated by x equal to tx k minus 1 plus c. For k is equal to 1. Okay. So what do we do? Now we can talk about the types. But before that, can we go to the next page? Okay. So the next one, I'll talk about the first one. It's called the Jacobi method. So basically, all that you do is rewrite. So to come back to that, let me first highlight it. So you have an ax is equal to b, and then you write it as x is equal to tx plus c. In this case, your x is a inverse of b. And in this case here, you can have zero and have b to be equal to, maybe let me say, I minus t of x. And so c equal to I minus of of b. So it is this idea that we use then to compute certain of the matrices that I'll talk about also later. First method I'll talk about, Jacobi method. So for the Jacobi method, you write matrix into form G where D is the diagonal L the lower triangle matrix of U is upper triangular. If you do that, then your system basically A1N into one split D, which is A1, A1, A22 up to ANN. Then you can do your L. You can do your L as 0 up and 0 minus into minus A. Then your U, you can write it as your U, you can write it as 0 everywhere here minus A1 to up to A1N. And this is A N minus 1. So you can rewrite your matrix in the form of you can rewrite your matrix in the form. When you do that, then how you can write instead of AX is equal to B, you can write G minus L minus U, X is equal to B. And then the Jacobi method says all you have to do is separate your diagonal entries from the rest. So dx minus L plus U x is equal to B. And then write your dx to be L plus U of x plus B. Now take your line. Then this gives you x and c x minus 1 plus the C. I'll call this a J. Where the Tj, where Tj is equal to D inverse L plus U, and Cj is equal to D inverse. And this is what we mean by the Jacobian method. Basically. We write it again as a fixed point. Any question? Proposition. 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 If A an n by n matrix is strictly diagonally and this before by rule the Jacobi method. Converges. So, any questions so far? Before I go to the next one, which is called the Gauss-Seidel method. Okay. The next method is called the Gauss-Seidel method. Okay, Gauss-Seidel method. So for the Gauss-Seidel method, what you do is a bit different from the Jacobi method. Is that the same way you have the A to be D minus L minus U. Unlike the Jacobi method, in this case, we only separate the upper from the rest. V in by U x equal to V, V minus U of x is equal to V. Then in that case, you can write, so, d minus L of x. Now we have d minus L of x is equal to plus b. And now we can write x to inverse of u of x at b. Here we can write out k. Here we can write k minus 1. So in that sense, as well, we have an sk to be equal to t. Let me call it g of x k minus 1. Sorry, d minus L inverse of b plus cg, where cg is d minus L inverse of u, and cg is equal to d minus L inverse of b. Okay, so if we want to study the convergence of these methods, why they converge, we'll have to talk of some other things, like the spectral radius, but we'll talk about them later. To go ahead, so this over the possessive over relaxation. Method 3. Relaxation. Relaxation. Okay. So for relaxation method, it's a way to generalize, right? To generalize the Gauss-Seidel and Jacobi method. Okay. So in that sense, what we do for a relaxation method is that I'm not going to go about how to derive it, but just to going to have an idea of what it is. In the same sense as we spoke about for the Gauss-Seidel method, okay? The Gauss-Seidel method. In the relaxation method now, what we do is that we introduce a relaxation parameter. We introduce a relaxation parameter. Omega. Let's call this parameter omega. Then what we do is now we have D L X D plus U plus omega B. Sorry, let me not add omega now. I want to add it to make it color. So we have omega 1 minus omega omega of D omega here. So in a similar sense, if you go back the Gauss-Seidel, you see that it's as if we are trying to improve the Gauss-Seidel method. And then when we do this, then it means we can write now a D minus omega L, and then 1 minus omega and then we have omega. All right, so I'm trying to write it in a way. Inverse plus U X plus omega. So let me see. This can easily become omega D minus omega L inverse of B. So we can write B and our K minus. And in that sense, the relaxation method SK minus 1 plus C relaxation method, where C is minus omega L inverse times 1 minus omega of D omega over u, we are omega times p. Of course, the question is how do you choose omega? How do you choose this relaxation? So, oh, no way. So, before that, I did the proposition that if you choose an n by n matrix, and if it is tridiagonal, non-singular matrix, whose diagonal entry elements are all non-zero, then Gauss-Seidel matrix are both either both both convergent. If they are both convergent, in the latter case, if they are both convergent, and then this is what I said I'll speak about it. So more precisely, the spectral radius of its iteration matrix is equal to the square of that of Jacobi's method. So finally, in the last part, what I'll do is I'll talk about this spectral radius stuff. And then after I'll give you some assignments for you to go and do. Now, like more programming assignment for you to do, but also I'll give you a reading assignment as well, because now that you understand how to do this kind of iterative methods as well, I want to see if you can send it to some known technique. Very popular common ones. You can read it and understand techniques. Very well-known techniques. Okay, so what I'll talk about is the lemma is if the spectral radius let me talk about the spectral radius. spectral radius. The spectral radius, which we write it as this, of the matrix A is defined by A is equal to the maximum lambda J, maximum lambda square lambda again of A. Theorem. So this theorem talks about the spectral radius is related to the norm of the matrix as follows. Theorem. If A is an n by n matrix, then 1, the norm of the matrix, the hidden norm of the matrix is A, the spectral radius square root 2. Spectral radius of the matrix is less than the norm of the matrix. So this is how the spectral radius is related to the norm of the matrix. I think I spoke about norm, right? So just in case you're unsure, the matrix norm, right, should satisfy 4, maybe 5. 1. If the matrix is 2, if it is 0, if and only if A is 0. That's all entries are 0. 3. A scalar and a matrix will give us this 4. The sum of the matrix will give us that. And 5. The product will give us that and that. Okay. So with that, we can talk of if the spectral radius gamma, if the spectral radius of T satisfies this, then I minus C inverse. And can be written as I minus t to the power minus 1 can be written as I plus t plus t squared plus is equal to the sum 0 to 0 to infinity. For any x to the power 0, the sequence x to the power k defined by for each k equal to 1 converges to the unique solution of x is equal to tx if and only if of t of course one of the other things that I said I wanted to address was one of the things that I wanted to address finally before I end this one is how do we choose omega? Okay. So theorem is the diagonal is not zero for each I want to add, then spectral radius EI greater or equal to absolute value of omega minus 1. This implies the method can converge only if omega is between 0 and 2. Another theory says that if A is positive definite, and omega is between 0 and 2, then the successive relaxation is the relaxation method. converges for any choice of initial approximate is same as positive definite and also try diagonal. Then the spectral radius of now is equal to the spectral radius of the Jacobian and is less than 1. And the optimal, no. Optimal choice. Optimal choice of omega for S1 is omega is equal to 1 plus 1 plus 1 plus 1 plus omega Cj squared. Okay. All right. So with that, we'll end here. I'll give you some exercises. Of course, there are certain things that you get to realize in the exercises that I'll send to you. One of them is if you are doing your these things, stopping criteria. If you are doing this exercise, you see that you need a stopping criteria. You need a stopping criteria on when to stop. And all this will be discussed after you have done the exercise. We'll discuss this aspect as well next week. So next week we'll have maybe a very long session as well. Today we have managed to make maybe about 3 hours. So next week we'll have another long 3 hours. Maybe we'll have maybe 4 hours or so next week as well.
So please,